Now we will look into the compute and memory complexity of deformable data over data. So that is one of the main thing that they propose, like it's faster, efficient, and require less compute, so and memory space. So we will initially look into what are the some of the bookkeeping points. So this NQ, key value, and heads channels, these are something we know. So this is S is actually, so if you have say different features like so this is will be say h2, h3, h1, h2, and this will be the summation of, so basically the summation of all the feature map across different level. The k is the number of points we sample across level, and l is the number of levels we have. So the first one is nc square for the projection matrix. So it's the symbol, right? So it's the symbol, the query key value projection matrix. So how it comes, nc square is, so it will be from c space, c dimensional to c dimensional, and you will have nc. And when you have a matrix multiplication like this, it's nc square, because there will be C multiplication, C minus 1 additions, and across C channels, and N, so NC squared. So this will be that. And the next one is the self attention Q K transpose, that is also similar, exactly similar. So you will have this will be your key matrix, this will be your query matrix. Similarly, there will be C computation required here for across nk channels and across nq channels. So it will be of order of nq, nk, and c. And the next one is once we have our say uh, nq, nk matrix, you have to softmax along the channel that will be of nq, nkj, and you have to do it along nq. And there will be m heads, so that will be nq, nq, m. And once after this you will have to multiply it along, right, along cv, like this is for the final projection matrix, right? Once you have nk, nq, you have to, so you have nq, nk, and then you have your value matrix will be nq, nc. This will be nq, nk, c, right? So this is what this corresponds to. So that will be the softmax plus weighting. And sampling plus interpolation is something that is very much specific to deformable attention. So we say, like, once we sample, we look into say for each point we look into k points, like, so they are telling, so each of these point have c channels. So we it will depends on the number of points we channel, and each channel, and for we do it for number of queries, right? Number of queries, for each query we sample k points, and each depends on the channel. And they say the cost of this is some 5, like cost of the bilinear extrapolation is some 5 times per sample. So this is from the paper. So it will be order of 5 nk in kc. So that will be the major computations contributing to the cost. And for memory, for you have to store the nq, which is the attention matrix, over m heads. So that will be a big memory matrix, say. So why it will be, suppose it was 23980, I'm telling it for deformable data. So you have a 23980 comma 23908 heads, so that's a big matrix, right? So uh, that is what we save in so when we come for deformable data, it become 23980 comma 16, say 4 cross 4, m is 4. So that is a big save in terms of memory as well. So let's see how so this equation is for the standard attention. This is directly from the paper. The paper have it just like that. So I can, so this is the attention weight, this is the value projection, this is the final output projection. And so we know that this will be the query projection. We know from top the query projection will be nc square. So here is nc square, and the same for nk, and so on. And the scores is, as you know, from it will be nq nkc, and the score is nq nkc, and the softmax is mnq nkc, like mknq mnknqm, and there is the softmax score plus multiplying by finally v. So this will be, c will be much larger than m, so that will be the dominant term there. And the output projection is also of the same type, nqc square. So this will be the total output, or this total computational complexity of this normal self attention which is used in data. And you can see that, so there is hw coming here, the number of query and number of key coming in, which is a big term, and so that is also coming in the memory as well, and you have to cache the nqcs. So these are the terms that are bigger terms contributing to the final, say, computational complexity. Now we can see the same for we will do yeah, we can actually look into specialization of debtor. As I said, for debtor, nq and nk are same, uh, because it's we attend to all the keys, right? It's to a if in our example it was this one, so we attend to all the keys. So this become s square c, and so this become sc square sc square. So this is the dominant term. And in cross attention we have, so how this term comes is, in cross attention we have nk is equal to 100, and nq say is s, which will be equal to h into w. So it will be, so this is directly from this equation, right? So nc square, uh, nc square n square. So yeah, you just add these equations, like directly put this value to this equation, you get this. Yeah, so but the main thing note here is this is dominated by s square, which is actually depending on h and w. So it's actually, if I have to write it in terms of hw, it will be h square w square c, right? So that is a big term. Now coming to the complexity of deformable attention with one layer, what we have is, so we have a predict and offset, right? So what predict and offset was, it was taking in the input dimension was nqc, and what we were outputting was mk points, right? So we were outputting m heads, 8 heads, 4 points. Actually we are not, we are saying, assuming this single scale, that is only one level, assuming one level. If we consider multiple level, it will come as 4 here. This is mk, this would have been l, but for this case we are considering one level. So that will be like that. So this would have been so c, nq c, c m heads k. So this will be corresponding offsets. So right, you have to predict two offsets. So this will be 2 nq c mk, and you have to correspondingly predict the weights, right? So this is the predict offset, and there is one parallel feed forward network that predict the corresponding attention weight, right? So that will be also there, and that will be also same side, but nqcmk, and this will become 3. So that is how the 3 comes there. And for the value projections, this can be uh, two possible way. Actually this is actually we can actually look into values directly from the queries. This is maybe what is happening in cross attention, and in in the encoder side we can actually pre-compute them, right? uh, it will be like, you have HW into C. Then for value projection you have C, so it become HWC square by the normal matrix multiplication thing. So yeah, and from we this one we have discussed above, like how it comes as 5. So here we discussed how it comes as 5, so the same it comes here as 5. So that and the output projection is also, we have what, NQC, and we have a C comma C, so it will be NQC square. And finally, so you just have to add up the terms. So this will be NQC square, this term, and the sampling term, this will be the value projection. So one thing to note here is, uh, in Detter, what was dominating was the cross attention term. Here the dominating term will not be cross attention term. So once we remove the non-dominating term, the dominating terms are coming as the output projection and this value computation. So these two are coming as the value projection, and the output projection are coming as a dominant term over the self-attention term, which was the case in Detter. So we have that here, and these are smaller matrices compared to what we have in Detter. So in the end, I will show a comparison. So you can see here, if you look into the memory, is M heads NQ across M heads, but in Detter it was NQ if Kn across M heads, that was big. Offsets, we have to solve the offset. And yeah, so this is, as I said, there is no, usually nk is equal to nq, that's why I write nq here. So there is no dense matrix to say that's a major memory gain. And yeah, so for encoder nq is equal to hw, decoder nq is equal to n. Yeah, so that is something similar. For multi-scale attention, it's same as what we discussed above. Instead, all the terms will have an L added to it, because now we are looking into multiple levels. So here S will come, because it's a summation of all the cells across different levels. But essentially the terms, it's adding a multiplying, say 4. So earlier it was 4, now it becomes 4 into 4 is 16. It's not a big deal, unless it's for query it might become big. But from they are not big compared, because it's a small multiplication. So this will be the channel, it's understandable. So now I can actually go into the final uh, where we are actually saving in deformable data. So if you look into the encoder side, the dominant term in encoder side, so you have this in data, and in deformable data it's of linear order. So here it's quadratic order, it's actually h square w square c. Here it's, if we are only looking on one layer, it's hwc square. C is usually 256, and h is h or s is actually big, right? So if even if I am using a small feature map, 34 comma into 34, it will become 1156, right? 1156 square into c. So this is much big compared to 56, even if you are using a smaller feature map. So this is a big win for deformable data. So even if you use multiple feature map, this term still remains. So we can actually use multiple feature map with less computation. So that is why it's a win, and that's why we can train easily. So the same comes for memory as well, right? So here it was nq nk mlq. So the number of yeah, the attention memory, this is a sparse attention memory that we need to unnecessarily store, but now we are storing a dense attention memory only. So that is good. And in decoder side, the self attention is same, right? Because the self attention is small. We in decoder, the first is self attention, self, it's same as in debtor. And cross attention also, there is something. Cross attention here actually depend on S, which is HW, but here we are not depending on that. Here we only depend on number of uh, uh, queries, keys, a number of places we look into, and channels. So that is also, yeah, kind of okay, I will say. Number of queries, number of points to look into, and channels. So in case of our, we had this as 300 for say 256. For them the S was H into W, right? And for them it was 100 into 256. So in that respect also it's kind of okay, maybe a win for us, as in the sense deformal detention. So the key point is we are able to reduce the memory footprint and uh, increase the increase uh, the way the attention weights are also good. Dense attention weight from computational complexities, memory or complexity space, it's good. Yeah, so that is a overall thing. And from a research perspective, you can see Ditter took 500 epochs and to reach 42 AP, and deformal Ditter with 50 epochs reached this one. And training on ImageNet took 325 GPU hours for deformable data, which is still high, but compared to data it was very much high. And the inference speed is also fast compared to 12 fps, and it converges much faster than data. So the original paper have a much more beautiful graphs explaining the stuff. So if you're interested, you can look into it. Yeah. So the first credits, most of the code I have looked into from the original paper implementation, which is neatly implemented, and Hugging Face also have a very neat implementation. It's also, if you're interested in actually using it, you can actually use these two. Yeah, that's it.